Hey, in the last video I was showing you the Photobottle, which is an open source photobioreactor designed for physiological experiments with microalgae, but you can also use it just for the cultivation of microalgae if that's what you're interested in. Might be something for, let's say you want to cultivate microalgae to feed corals in your coral tank. Like the Photobottle would be a perfect way to do that, because you're actually able to assess whether or not your culture is healthy or not based on its growth and photosynthetic parameters. Today I'm actually working on Photobottle version 2, and this is sort of getting more advanced into actually these photobioreactors. What I'm trying to do is make a photobioreactor that I sort of seem is a sufficiently easy to use and also advanced photobioreactor. So I'll give you an idea of what I'm working on at the moment. So this is the Photobottle version 2, which I'm currently working on. As you can see, we've still got that front mixing motor on the version 2 of the device, and that's just got the sort of the magnetic pieces to spin a magnetic stirrer that's inside this glass container. For some reason, when I was designing this, I didn't make it long enough for the motor, so that's something I'll have to fix. But as you can see, the scaffold is completely different. We've got these metal bars connecting all the 3D printed pieces, and the idea behind this is that what I want to do is make sure that the time to take to print all these parts is as small as possible. So because the device is significantly larger than the previous one, let me grab you the previous Photobottle. So on the left here now, you can see the previous Photobottle. That's my cup of tea, so don't worry about that. But then we have the new Photobottle, which is huge in comparison. So this is this first Photobottle was 250 milliliters of volume here, but what we have in this is probably around about 1.5 liters in volume. So then to start off with what we're adding here, we want to have temperature control. A lot of my experiments had temperature controlled rooms, but for this one I want to have the temperature controlled by the photobioreactor itself. So to do that, what we have on the right hand side here is a fan that's on a slider, and then we also have in my box here is a Peltier module that just fits in on top of this fan here. I've got to get some sort of a thermal glue to actually glue that down there, but that's what that will do. And then the idea is, once the Peltier module is on there, you just slide in the fan like that and push it up against the edge of the glass here. Tighten in this thumb screw here, and then you have the Peltier module pushed up against the glass. The reason why I haven't gone for it underneath the photobioreactor is because if you put it underneath, then if you get any leaks from the photobioreactor or spills, then all your electronics for temperature control will be in water. So that's what you're trying to avoid here. And then, so that's going to be on both sides. At the moment you can see this slider is not the best, so I'm going to have to improve the design of this to make sure that when you push this into the glass here, all of the Peltier module is touching the edge of the glass, and that the slider doesn't move too much. Because as you can see, there's a bit of shake in that, so we've got to fix that. Then you can probably see these two motors here, which are these are going to be for the Thermostat mode. So the idea being that you want to keep a constant density of microalgae so that the transmission of light from the growth lights is always constant. So to do that, we've got this two pumps, one for pumping in microalgae, pumping in fresh media, and one for pumping out microalgae, like to just do a waste bin. And that way, what we can do is, because we have an optical density sensor on this photobioreactor, that means that we can basically say that if the density increases, then get rid of some of the microalgae and put in some media. And for that, you're probably I'm going to have to implement just a PID controller, which allows you to sort of ensure that we don't just get to a certain value, pump out a ton of microalgae, then let it grow, and then pump out a ton of microalgae. Because what we actually want, if I get my pen here, so let me just draw what we want to happen with the density. So here we have our graph here, and this is time, and then we have density. And the idea being that we want to have a constant density over time. So this is our turbidostat mode. And if we don't have a PID controller is actually trying to adjust the changes in density with the two pumps that I showed you to make sure that it's as close to this value as possible. But if we just say if the value is over a certain point, so let's say it's 5% above the value that we've desired, then what we'll actually see is the algae will grow up to 5%, then it'll dilute it down to the value, grow to 5%, dilute it down to the value, and it'll just go like this, these oscillations. But we don't really want that, we just want stable density. So that's when a PID controller comes in, PID. It's like position integral derivative or something like that. We've got to work on that. And that's got to be the same for the temperature control, so you could just sub out the density here and just put temperature, and then that's going to be not turbidostat mode, that's going to be thermo. That's going to be our thermostat mode. So that's what we've got to work on. So for this temperature control here, we're going to actually have one of these on either side, so that I'm thinking that if we apply temperature into this side here and this side here and then mix in the middle, we should be able to get a like a good distribution of heat or cold, depending on what we want. Because with these Peltier modules, that's the best thing about them. You reverse the polarity on them, and then you actually can get cold. So we can heat up the culture and cool down the culture with just one device, which is great. And these things are quite cost effective as well. So then it brings us to the bubbling. We're actually using the same motor as what we have for the original pheno bottle. Pretty much in the same position as well. But what I want to do is also add the ability so that we can add a what's it's called is a solenoid valve. And the idea of a solenoid valve is that we can connect up a CO2 supply and then just have the 12 volt system turn on and off the solenoid to bubble in air with CO2, rather than air with this pump here, because we're just pumping in air into the system, which is fine, but you want to have that sort of customizability. Then we've actually got a custom-made motor control circuit for this new pheno bottle. So this is motor, and also we have pH, so you can plug in a pH probe here, and then we also can let me just put that up like that. We can put a BNC connector here to a pH probe, and then we can measure pH with this Tinsy microcontroller here. On the previous pheno bottle, what we had was a 15 volt supply, a 12 volt supply, and a 5 volt supply. The 15 volt supply was just powering a single actinic LED for the fluorometer. But for this one, we're just going to have a 12 volt supply for everything. So you plug in a 12 volt barrel jack into this barrel jack connector here, and then that's got some reverse polarity protection, and then we have a 12 volt output, which I'm going to take to another sensor that we need. Then what I've made here is basically it's it's inspired by the Adafruit motor hat for the Raspberry Pi. I think I have a... So I have this motor hat here for the Raspberry Pi, and I've put the header on the wrong way. This was years ago. But the idea is that you can plug this onto the top of a Raspberry Pi, and then it gives you 4 motor outputs here for the different motors of the Photobottle. And this is what we actually used for the Photobottle, the first version of the Photobottle. But what we actually want now is, because we have way more motors and we have lots of lights, and we want this kind of customizability. So I've used the same motor controllers. So this is a PWM output, so we can put out different PWM signals, and then we have a motor controller here on this chip here. And that's the same for the new Photobottle circuit, but instead of that we have 3 in parallel, and these are able to power up to 12 motors. So we have the fan, so for each of the heat sinks, so the heaters, these have a fan as well, so we can actually dissipate the heat to make them colder, so that this is more efficient. Then we have the Peltier, which is this device here. We have the, let me see if I can zoom in. Focus. Yeah, we have the air control, the mixing control, so that's bubbling, mixing. Then we have pump 1, so this is going to be either the input or output. Pump 2, input or output. Pump 3 is going to be for the fluorometer, because we need to pump through. This is actually going to be for the fluorometer and the optical density sensor on this one. So you pump through the microalgae through a flow-through cuvette for the optical density measurements and for fluorescence measurements. We have the second Peltier, the second fan, and then we have this red, green, blue outputs here. So for each of the individual RGB channels for the growth lights, we have these separate outputs, which is pretty great because we're able to actually control them a lot easier than in the first version. But anyway, we've also got these I2C connectors here. So if we want to connect up a certain different device, I2C device, then we can actually change the I2C address of each of these modules here, and that way we make sure that in the future we don't have any problems with conflicting addresses for I2C devices. So that's the motor and light control circuit, and I think it should be pretty good. I haven't tested it yet, but that's what my plan is today. So next up we're going to look at this LCD screen which we've got on top of the photobioreactor here. When we first started working with the photobioreactor, there wasn't really that much need to have a LCD screen, but just something to display the parameters and also the whether or not the motors are on or how they're functioning would just be great to see, just a visual display on this screen here. So that's just a TFT screen. I've got it blue tacked in there at the moment until we find a more permanent solution. But these things are great. It's pretty easy to set up, and that actually will work with this motor control circuit here. I've got a TFT connector down the bottom here that I've made, and you just plug in the wires to that and should all work. As for the RGB LED panel, we have this panel that I made that's pretty much the same as what a RGB LED strip of 1 meter would be. So you have these individual RGB LEDs in groups of 3 with some resistors, and then we just have some inputs that are on the back here with a display LED. One second. So we have these 3 inputs here. So we have the red, green, blue inputs. Let me just see if I can focus. Yeah, so we have these red, green, blue inputs, and we have some indicator LEDs, which are the ones that are going to go to the motor and light controls. So that's on the back there, and then we just plug that in for controlling all these LEDs. So yeah, as I say, this is pretty much equivalent to 1 meter of high density LED strip, but composed within something that's about 20 centimeters by 20 centimeters, or a little bit bigger than that. So we actually get quite bright display from this. And that just slides down into here, like that. And the idea being is that we can move the LED panel further forwards. If let's say we have a really dense culture, we can actually, because we have these slots here, I've just modified one of them to fit this panel. Because originally I was going to use some aluminium sheeting, but then I thought, let's just make the whole circuit board here. But the idea being that we can actually move the LED panel steps forward, so that we have this, if we got a really dense culture, we can move it right up the front here and get the LEDs right up close to the culture. We can get the maximum brightness from the LEDs, or you can put it further back if you want to ensure that there's like a very diffuse sort of lighting, so homogeneous lighting onto the culture. Because the further you move away from the LEDs, you don't get any hot spots. But if you move it right up here, you might get some hot spots. But there's just the option to do these kinds of things. And then, if I move around the back here, we've got the best thing of the whole thing is this new Raspberry Pi. And this is the 4GB, 4 gigabyte of RAM, gigabytes of RAM. And this is running on USB-C, which is great. And the thing is so powerful. So with the old version 3 of the device, I would do all the coding on my Windows computer and then transfer it over to the Raspberry Pi just to test it. But now we can actually do all the coding on the actual Raspberry Pi, and it works really, really well. And that just has like the same thing. So we've got these USB outputs, which we can connect our Tinsy, which is for the motor and light controls. We've got Ethernet, and we've got a few other display things like HDMI displays. But these kinds of things, you know, if we want to upgrade the device in the future, and let's say version 5 of the Raspberry Pi comes out, or this is the kind of thing that all we have to do is swap it out. You know, if you are using the Photobottle, the first version of the Photobottle, then you could actually just swap out the version 3B for the version 4B, and you'll see huge performance increases from that transition. But let's say you had a commercial photobioreactor, it would be much harder to upgrade the device over time compared to how easy this is. Like, it's just swap it out and put it in. So there's sort of an incentive to this open source design where you can just make and upgrade the device yourself over time. So that's pretty much where I'm at the moment with the version 2 of the Photobottle. Let's have a quick look at what the user interface is looking like. Alright, so I got that interface working now. So if we just run it, it comes up with our interface here. And as you can see, there's a lot of white space in this first screen. That's because what we're going to put in here is a nice graph, and then have some features so we can select parameters like OD, fluorescence, and that way we can actually track that over time. The way I've sorted it out is we have these tabs here. The second tab has got the lights, motors and pumps, and that allows you to control, for example, the duty cycle of each LED. And then if we come over to the right here, we can test it, or we can change we can test that, and then we can change the frequency of the PWM signal. This kind of features and stuff is great because with the Raspberry Pi we didn't have access to these kinds of things, but with this Tinsy microcontroller we can do all that. It also features, rather than the Raspberry Pi, we had 8 bits of digitization, which we could change for, let's say we want to change the speed of the motor, then we just change an 8-bit value to increase the speed of the motor. but for the Tinsy we actually have 10 to 12 bits of digitization, and that way we can actually fine-tune the motor controls to actually bring up the mixing intensity to whatever value we really want, because I found the mixing intensity was just a bit too coarse with the original 8-bit system. And then we have down the bottom here mixing controls, bubbling motor, peristaltic pump, culture in, whatever. All these kinds of things, you can turn them on, you can also reverse them, because what happens is with the motors you get, a lot of them actually have polarities that are switched, so it's actually kind of annoying, but just the reverse function will just allow you to say, yeah, I want that motor actually to run in reverse, and then just set the value of whatever you want the motor to run at. In terms of environmental controls, we're looking at this temperature, pH and density settings. So here we can actually just set up a constant temperature of like a thermostat mode. You enable it, you set whatever temperature you want the culture to be at. The same goes for the pH, which you can just enable whatever pH you want to run at. We also have a calibration interface for the pH probe. So that just works by selecting the calibration. So we have a 3-point calibration, 4, 7 and 10. And then we just has once you click that you select you want to calibrate the low, the pH probe enters its calibration procedure. It'll display what the current calibration value is, so you just put the pH probe into a pH 4 solution, and then once it gets to a stable value, then you just click set, and that'll all update in the software, so you don't have to worry about that. And you just continue that for each one of the calibration settings. So if we get out of that, we can also come over here to the turbidostat mode, enable turbidostat mode, set the density of the culture that we want. We can also calibrate the pH sensor, calibrate the optical density sensor to 100% transmission. And this is important just before starting the experiment. We want to make sure that all the sensors are calibrated properly. Then we come up and we have these settings. We can create a new file with some default values. Let me just get that so you can see. So we can create a new file. We can program from a predefined template. So I'll create some templates. That way when the instrument comes, you can just click whatever template you want. It might be a pH template. So you can do it also from here. So pH stat mode, thermostat mode and turbidostat mode. You can set that all up and it'll already have predefined values, and you just have to click play. You can open up some old experimental settings that you had, or save the experimental setup that you've got at the moment. You can run the experiment, pause the experiment, so this will just stop everything and just pause it so you can do something that might have had a problem. Or once you finish the experiment, you can stop or abandon it. And here we just have some settings, so you can come up and set some things like there's the calibration interface, optical density, same as before. We also have some hard limits on the mixing speeds and motors and pumps. So the idea here is that we don't want to run the pumps and everything at full tilt. We don't want to have them running at maximum speed all the time. So we just set like a max limit. We have the lights here, which we want to run, let's say at 75% rather than running them at full tilt, because then they'll burn out faster. So we just want to set some sort of a limit there. You can always change that if you want to change it, but it's just sort of in these background settings just to make the device work for longer and work better. And then finally here we have probably the most important parts is this temperature control. So the idea is that we want to set a max temperature of the system so that people don't just accidentally set a temperature of, let's say, 80 degrees. And that means that the Peltier module is pretty much running all the time to try and keep the culture at 80 degrees, just because they've done it by accident. We wanted to reduce the amount of fire hazards with the Peltier module, because these kinds of heaters and stuff, it's always just a bit more of a risk, especially when around water. It's all 12 volt anyway, but you just want to reduce the risk. And then we also have a timeout for the Peltier module, and I'm not sure how this actually will work, but I think that the Peltier module will just turn on whenever the culture needs to be heated up or whatever, using the PID controller, which I showed you before. But I want to set a timeout for it so it doesn't just run. Let's say the Peltier module isn't pushed up against the edge of the bioreactor. So if we just look here, you can see how the system is all pushed up against the edge of the glass here. But let's say the Peltier module is out a bit. That means there's no contact really with this part of the glass here. And the Peltier module would just turn on, try and heat up and heat up and heat up. But in reality, it's not touching the glass, so it's not going to heat up anything. And I just want to set some sort of a timeout for that. Just to say, like, if you've been running for 3 minutes or so, then I want to notify the user that something's not right here, you know? So that's just some sort of hard limits in the settings there. And that sort of gives you an idea of the user interface so far. We've got to add some way more controls and actually see if we can get some sort of graphing interface up there as well, because we have to do the network processes next. But that's what we're working on. So that kind of gives you an idea of what is happening with the Photobioreactor version 2. If you want to know more, you can always email me and I'll just give you an update or go from there. But I'll keep you updated in the future once I start doing some experiments with the device, just to see what's happening, you know, see how the experiments are running, see how these sort of controls are working, and especially the PID control, because that's something I haven't done before. So we'll have to figure out how to do that. I think it shouldn't be too difficult, but we'll go from there. Alright, I'll catch you later.